And now I will continue with some other perspectives of this result, what this really corresponds to, how can we come up with this kind of a result, and are there other methods to come up with the same result. For that, I will start from this equation, which is the difference square, the energy of the difference square, and instead of x optimum hat, I will put x hat only. So, and therefore, if I don't use the optimized prediction, this will not be the minimum. It will simply be sigma d square. It's not the minimum of that. So I will start from that. Let me write it again. Sigma d square is equal to expected value of, let me copy it from here, x of n minus x hat of n, in parentheses, squared. X of n minus x hat of n squared. This is the prediction error, but it's not the optimum because I'm not claiming that x hat is the optimum linear predictor here yet. And when I do that, let's now expand this square. That thing will give you expected value of x square minus 2 expected value of x and x hat n, and plus expected value of x hat square of n. Okay. In general, this is the actual way of writing the same thing. Now, if you make the substitution that x hat of x hat of n is equal to summation, let's say I from 1 to capital N, hi x n minus I, but these hi's are not the optimum filter coefficients yet. Okay, so they are just filter coefficients. With this substitution, this thing becomes sigma x square, because here we have sigma x square. I'm assuming again zero mean. It's Rx0, you can say, minus 2h times Rx. This is H transpose. It must be. One of them must be transpose because it will give you a scalar. And plus H transpose Rx inverse H, which was essentially the result, but it has something else. You see, in the previous minimized version, the sigma x square is here, and there is a minus sign here with this kind of an expression, whereas now I have a plus sign with the same kind of an expression, but I have this thing to be subtracted. This thing, this new expression is sigma d squared, and it's not equal to sigma d minimum squared because I did not use h optimals. I just use any h. Now, how can we minimize this? How can we look from the perspective that this sigma d square thing should be minimized with respect to h? With respect to h vector, you can say, but h vector consists of h1, h2, h3, etc. Now, if you look closely, you see that in this expression, this is a constant term. So I'm trying to minimize this with respect to these h's. This is some constant term. We cannot touch that. And here I have h, like minus 2 times h times something. So there is h. And then here I have h and h, which is something like h square. Okay. So it resembles something like A plus BH plus CH square kind of thing. Okay. Of course, it's not scalar. It's not a scalar equation. It's a vector form. But the situation is like that. And I'm trying to emphasize the fact that this h thing here is in the form of a quadratic. There is h square. And because of that, when you draw this thing, this expression in 2 dimensions, if you try to plot it with some reasonable Rx and this Rx inverse, of course, you have to substitute some actual things like this Rx matrix must consist of, in 2 dimensions at least, it should be something like R0, R1, R1 and R0 like this, where R0 is greater than R1. You have to choose it that way. And this Rx vector should be like R1 and R2. Okay. Then you may make a simulation to see that in 2 dimensions at least, it looks like this. How can I try to plot it? This is the one axis, this is another axis, which are orthogonal to each other. Okay, so this is, I'm trying to visualize something 3-dimensional, okay? And this is also orthogonal to the plane of the previous 2 axes. These axes could be called as H1 and H2 in 2 dimensions. And this thing is sigma d square. And when you plot it, it looks like this. Something like this. So this thing is this kind of a shape, okay, a quadratic 2-dimensional shape, which is extending. And there is this minimum point that corresponds to H1 optimum and H2 optimum points. So at the point of H2 is equal to H2 optimum and H1 is equal to H1 optimum, this surface, quadratic surface of sigma d square, reaches to its minimum value. And that is the place that we are actually looking for. And there are numerical ways to do that. That is something that I can say. This is, by the way, a function of course, h. So how can we reach to the minimum of a quadratic curve like this? We know that there is steepest descent, for example, which calculates an approximation of the gradient at any starting point, at any initial point, pointing towards the minimum. So you go a step size and you reach to the new point and you evaluate the gradient again and you reach to this point, etc. Of course, it's a numerical value of steepest descent is a numerical way of doing things. And for that, you have to evaluate the gradient and you have to decide the step size to proceed. If the step size is too small, it will take a long time to reach to the optimal point or to the vicinity of the optimal point. If the step size is too large, you will quickly converge, but then you will overshoot the optimal point and then you will have to come back and overshoot again. So there are lots of numerical methods that are explained in, let's say, adaptive filters courses. if you have taken them or if you are familiar with those things. But the gradient that you are trying to estimate is actually this, which is the derivative. Oops, sorry, it's not h. It is minus 2 Rx plus 2 capital Rx times h is equal to 0. But you can use either these as a step size for updating your filter coefficients. Like in the previous stage of n, you had h of n. That was an initial starting point of some filter coefficients. And then you update them with respect to a coefficient. Alpha over 2 is the coefficient. I'm writing it as alpha over 2 because I'm going to write the gradient of this here, and inside the gradient, as you see, everything is multiplied by 2, so they will cancel, and this update will become h of n minus alpha times minus Rx plus Rx times h, for example. Yeah. So this is an update, and these updates are approximated because we don't really use precisely the gradient, but an approximation of the gradient, etc. There are lots of things to do here in the steepest descent. You can use least mean squares methods for adaptation, and using the iteration from hn to hn plus 1 and then hn plus 1 to hn plus 2, etc., it just converges at a point which corresponds to the optimum h points that would correspond to this point. This I'm explaining this not so that you do it and you implement it. You may, and that would be very nice actually, but I'm trying to show you what this really means. So other filter values, for example, this value of H1 and this value of H2 would correspond to a larger difference or error variance, error energy, because it's not the optimum prediction error, prediction filter. You optimize the prediction filter so that the error is minimum. That's one way to look at things. And there are lots of things that you can do, as I'm telling you. Now, but we don't have the time to go into the details of this, and it's not our business anyway. Our business is more like the optimum gives you the solution to this equation. This is equal to 0. We'll tell you that h is equal to Rx inverse times lowercase rx, okay? That is the solution, but we are trying to solve it now. And there are methods to do this, and there are visualizations to do that too. So this is an important visualization. Of course, I'm giving it only in 2 dimensions because I can only represent in 3 dimensions, one more dimension. I cannot make any visualization for the 3rd order filter, prediction filter. Now, the next thing is that I want to briefly mention about is called the Levinson Durbin recursion, also occasionally notated as only the Levinson recursion, because yeah, in some books they don't mention about the Durbin. It must be 2 scientists or something like that. I'm not pretty much sure about it. The Levinson recursion is taking 2 equations. One equation is the following: Rx times h is equal to lowercase rx, which is here, okay? But at the same time, it also, the equation also provides us with the minimized error energy, which is sigma d. Actually, this is minimized, of course, and this is optimum, by the way. Sigma d square is equal to sigma x square minus this summation minus, where was it? It was here. I'm trying to rewrite this equation. Sorry, this equation, hi optimum, the summation hi optimum rxi, which will give you this equation. This is sigma d min square. So I'm writing it here again. I from 1 to n hi optimum times rx of I, which could also, of course, be written as sigma x square minus, which one should I prefer? I'm trying to think of it. Let me write it like hi optimum vector transpose times no, it's not capital Rx, it is the vector form of Rx. We can write it like this. Okay, so we have two equations, this and this. This is equal to sigma d square minimum. So how can I combine these two equations into one set of equations? I will write it in an explicit form first, because the combined thing in a compact way is quite unavailable for the time being. All right, it looks like this: Rx 0, Rx 1, Rx up to n, not n minus 1. This time it's up to n, because previously it was only Rx1 to Rxn inside here, but now it starts from Rx0 and it further extends to Rx of n. Let me first write this, then you will make better sense, hopefully, about the equation that will come out. Rx of n, Rx of n minus 1, again Rx of 0.
I have a question, Professor.
Excuse me?
I have a question. What is that underlying thing? That's
Under
underlying Rx.
underline means it's a vector or a matrix. For example, here, hi optimum with an underscore, underline, it means this is an hi vector. This Rx underline is an Rx vector. This capital Rx underline means it's a matrix, because I'm using uppercase for matrices, lowercase for vectors. And since I cannot write in boldface while I'm writing, I'm just putting an underscore to show that it's either a vector or a matrix, to notate it that way. All right. So this times, here this is an interesting vector. It has 1 here, because that 1 will contribute to this equation, and the rest is h1 up to hn. Okay, and that will be equal to, normally this is equal to 0, but that equal 0 part is, maybe I should draw it like this. This part, if you think of it, times this part will give you 0. But with the others, we have something else. We have this thing to be equal to sigma d square, of course minimized, and the others are 0. Okay, what I did is I just combined this and this equation into one single vector matrix equation. And there's a name to this equation. It is called autocorrelation normal equation, abbreviated as ACNE, autocorrelation normal equation. This is a very well-known equation in the concept of control theory in signal processing, as well as here, of course. And this thing called Levinson-Durbin recursion is not unique to predictive coding only. It's used in solving autocorrelation normal equations. It's a generic way of doing things. So you may encounter it in other disciplines, particularly in control theory too. Because we have the autocorrelation normal equations, we encounter this in a lot of places. Now, this autocorrelation normal equation, if you have this kind of a construction, it starts from the smaller autocorrelation normal equation, and there is a methodology, there is a recursive way of making it larger and larger. And the smallest is this. When n is equal to 1, we have this autocorrelation normal equation, Rx0, Rx1, Rx1, Rx0 times 1 H1 is equal to sigma square 0. This is the smallest autocorrelation normal equation that you have. And when you have this equation, and when you solve for this, you see that H1 will be equal to, by the way, I'm sorry about this, but these are negative. Let me put minus signs here. So, yeah, that is something that I have forgotten. So we shouldn't really put H1 here. I have to put minus H1, or the minus of it I can give a different name. For example, I can say A1. Okay. Usually this one H1, negative H1 is notated as 1 A1 in the recursive manner in order not to be confused about the negative signs, and A1 is found to be something. But that H1 is Rx1 over Rx0, or A1 is equal to negative of Rx1 over Rx0. You can say, same thing. And it also gives you the variance, the error variance, sigma d square, to be equal to 1 minus A1 square or H1 square times Rx0, okay? And this Rx0 is sigma x square, as we know. A1 square is equal to H1 square, and 1 minus H1 square times sigma x square is, it was the previous solution, but we wrote it in a different way. Instead of this A1, we wrote it as rho 1. But remember that H1 is equal to rho 1, right? This H1 here is equal to rho 1. So in our previous methodology, we wrote it as a 1 minus rho 1 square times sigma x square. So it's the same thing. This is the starting point of our iteration, which gave us the same result, of course, of the first order predictor. But how can we extend it to larger and larger matrices with longer and longer filter coefficients? This is only one filter coefficient. If you put two of them, it will correspond to a 3 by 3, and a length 3 vector is equal to a length 3 vector consisting of sigma d square 0 and 0. Now, there is a way to come up with an update of H. From the previous H's to the current H, there is an update. So the new H1 will be an updated version of the previous H1, and the new H2 will be a completely new H2. Okay, it will be an incremental new information. It emerges. H1 is updated, H2 emerges, and sigma d square also gets an update from the previous by making it larger. When it becomes 4 by 4, it will use H1 and H2 from the previous solution, from the solution that we just found, and then it will update them. H1 will be updated, H2 will be updated, and a new H3 will emerge, and sigma d square will be updated. So every time a new parameter comes into the picture, the old parameters are updated, and this parameter of error also gets updated. It's also a parameter. That's how the update works. And the update, I will just very briefly mention about the idea about how that update is formulated. It's just pages long derivation of Levinson recursion. And I'm sure if you check the internet, you will find this derivation. But I'm not sure whether you will make a thorough understanding of that derivation without a professor tutoring you. Otherwise, it will be difficult, but you may look at that. You may check that if you wish. The updated iteration comes from the fact that you can write Rx at size, let's say j plus 1 using the size j Rx like this. The autocorrelation j by j size matrix is there. So it's a matrix, and it's augmented with a is this thing? It's this matrix here is augmented from the right hand side with a column vector, and that same column vector transposed, let me put a T here, transposed will become a row vector. It is augmented from the bottom, and there's a corner side here which has to be Rx0. It's a constant coefficient. It's not a matrix or vector or anything. So now this new matrix becomes j plus 1 by j plus 1 in size. But it could also be written, actually it's the same thing, as putting the Rx0 to the top left corner and using the matrix of Rx of j at the bottom right corner, augmented it from the right hand side with now this must be different in notation, row j, row xj of transpose, and this is row xj. There's, as I say, a difference between Rx and row x because if you write this thing in a large manner, it looks like this: Rx j plus 1, Rx j, Rx j minus 1, going all the way down to Rx 1. Sorry, Rx 0, excuse me. And then I have Rx j, Rx j plus 1. What am I doing? Excuse me. I just have to erase. I'm sorry about this. I already messed up with the right hand side of the equation. Actually, this is of course Rx0, Rx1, all the way to Rxj and Rxj plus 1, and then Rx1, Rx0, all the way up to Rxj minus 1 and Rxj. Okay, more like this. And this goes to Rxj and then Rxj plus 1. After Rxj becomes Rxj minus 1, this is Rxj. This goes down to Rx0 and Rx1. And this is Rx1 and Rx0. Okay, so it's a huge matrix like this. What I'm doing is let me use it in blue and let me use the dashed one. I'm first using it from here to here, and I'm calling this as Rx of J matrix. And the other one, for the second equation, I am using this part. Okay. So if I use the blue dashed one, then it will have to be augmented with this one, which is Rx of J. As you see, it starts from J plus 1 down to Rx of 1. And it's transpose Rxj plus 1 down to Rx1 as Rxj transpose, this row matrix. And this corner is Rx0, this one. Or I use the orange dashed matrix as here. And on top of it, row X J transpose is from Rx1 to Rxj plus 1. So rho and R vectors are just interchanged in the orders. One of them is from the first to J plus 1. The other one is from J plus 1 down to 1. Okay, they are in reverse order. So thinking of this together with the right-hand side equation, like we have a vector here is equal to something, etc., depicts the top part of the vector and then down part of the vector, and it makes an iteration. It causes a recursive way of making updates of the solution of H from here. And that those updates, however, I will give you the algorithm. I want to give you the algorithm. So I don't show the derivation from this point on, which will require quite some minutes, a lot of minutes probably. Instead of that, I will give you just the algorithm in case you may want to use it. The algorithm of this Levinson recursion is as follows. You say that A1 at first iteration is equal to minus Rx of 1 over Rx of 0, and sigma d in the first iteration square is equal to 1 minus A1 square times Rx 0. So you start with this one, step number 1. And then for j from 1 to n, you do the following steps. You first say that a j plus 1, excuse me, I have to use a new notation here. Let's not say aj, but let's say kj, because this is k1. Okay, the reason that I'm introducing new all the time new parameters is that k1 is equal to a1, or a1 becomes k1 at the end of this process, the first step. But after every time I first update or evaluate a new K1, and according to that K1, A1 will be updated. And according to K2, A2 will be updated. So it's not single shot update as in the first stage of the algorithm. I have to put the lines of the for loop as follows. kj plus 1. So now I evaluate k2 to be equal to rj matrix transpose times aj. It's not matrix, it's a vector times this vector. So transpose times this vector will give you a scalar divided by sigma dj square. So the jth sigma, for example, if you are evaluating k2, it means j is equal to 1. So you are going to use sigma d1 square, which is already evaluated here. So you know it for k2. And this is equal to, in explicit form, Rx j plus 1 minus summation I from 1 to j ai from j times Rx j plus 1 minus I. It looks awkward, I'm aware of that, but it comes, all these equations comes from the sub-matrix depiction, and we didn't see the derivation of these things, but they are available, divided by sigma dj square. And after that, after finding this k, which is an incremental thing, I of j plus 1, the new j, for example, for 2, will be equal to ai from j, that is from 1, in other words, plus the increment. The increment is this k j plus 1, which you just evaluated one line above, times a j plus 1 minus I. Now this may look a little bit awkward. We don't need actually parentheses here. So let me remove the parentheses, because I'm using the parentheses for the vector-wise things. This is just j plus 1. Let me just write it like this. So if, for example, j is equal to 1, then j is equal to 1, I was also 1. So j plus 1 minus I also becomes 1. So a1, 1 you are using again. So this kj is using this, and it is also multiplying it with k of j plus 1, and it's increasing the value or iterating the value of aj to aj plus 1. When j becomes larger than 2, of course, these will start getting more and more complicated. Which a you are choosing, picking, becomes a little bit complicated and cumbersome, but it's there. And the one which emerges, which didn't exist before, which is a j plus 1, j plus 1, that is the a2 of 2, the new coefficient, which is the negative of h2, is equal to actually k j plus 1. So it's there. That is, now it can be assigned to become a2 or a negative of h2. But first I used it to update the other a1 or h1. And then we also update the error, prediction error, which is cd j plus 1 square to become 1 minus k j plus 1 square. So as you see, times sigma dj, the previous prediction error. So every time the previous prediction error is scaled by something which is less than 1. As you see, this thing is 1 minus something positive, which means it's less than 1. So it's reducing. When you monitor this, you notice that sigma d for different j, sigma d square consistently decreases, but it decreases slower and slower after some time, like this. Of course, it will continue to decrease. It will never increase. It means that if you overestimate the prediction size, the linear prediction filter size, you don't do anything wrong. It means that you're just overestimating the system, and you are doing complicated calculations. But it will not worsen the performance. The performance will not deteriorate. It will just not improve a lot. All right, so this is for 1, 2, 3. So this is the J, 4, 5, etc. And these are the sigma D1 square, sigma D2 square. Now, if you look at this kind of a shape, you notice that from sigma D1 square to sigma D2 square, there's a significant amount of improvement in prediction error. The prediction error is reduced quite largely. But after some time, the improvements become marginal. So where do we stop? The place to stop, which helps us to estimate the prediction order. So let's say prediction order estimation. It's heuristic, by the way. This is not the exact solution, because there's no exact solution. These are all statistical. It's known as the Akaike. Let me write it again. Akaike information criterion. AIC. This Akaike information criterion is just a heuristic, and it's a scientist, I think Japanese scientist's name, which gives you some overfit. So the order that this finds is usually a tad or at least one larger than the actual one. For example, if Akaike information criterion gives you the order is 7, it may be 6. But it's an upper bound anyway. And it goes on like this. The Akaike information criterion, it's a function, numerical function of I and C for general ARMA models of autoregressive I and moving average J. So we don't really need this J here. Let's get rid of it because we don't have the moving average model. We are only using the autoregressive model here. As you see, Akaike information criterion is quite a good or generalization of the model order. It's not only specific to autoregressive models as we are doing, it's also for autoregressive and moving average. It's equal to N, which is the number of samples used for estimating the variance. It's like the how many samples did you use to estimate sigma. It is a variance, sigma square is a variance, and how do you estimate it? You take the squares and you divide by n, right? That n, how many values you're using for the estimation, it appears inside here. But actually in the incremental way, it becomes quite insignificant. Natural logarithm of, so n is that one, the number of data that you use for making estimations. Sigma ij square, where j is again obsolete for our case, plus 2i plus j, again j does not appear in our case. All right. So I is like the numerator order of the moving average, and J is, sorry, I is, yeah, I is the numerator, excuse me, I is the denominator, J is the numerator order, but we don't have the numerator, so we don't have J. We only have the denominators. And sigma is the variance, or the mean squared error that we have. For our case, let me write it in a more simple form. A Kaiki information criteria of I is equal to n times ln sigma I square plus 2i. Excuse me, 2i. Now, what we see here is the following. N is constant, okay? It's the number of samples that we use for the estimation. So it's there, it's constant. This is telling me that I'm taking the logarithm of these values. And the logarithm of these values, as you see, becomes smaller and smaller. The numbers are becoming smaller and smaller, so their logarithm is also decreasing. But meanwhile, as J, here I say J, but this time it's I, of course. The index I, when it increases with 2i. So what we really have is the logarithm of that decreasing thing. From here, there's something decreasing. And from here, there is something increasing, 2i, with a slope of 2. So they are adding these two, which is telling me that it first decreases and then increases. The summation looks like this. And we stop at a point where it starts increasing. This is the optimum I value over the I-axis. This is how the Akaike information criterion works. And very interestingly, it also has its own recursion. You don't have to plot these and overlay and see where the minimum is. While you are doing the Levinson recursion, you can also iterate the Akaike information criteria by evaluating the previous Akaike information criteria from the previous stage, starting from 1, for example. Let's call it I minus 1, the previous, plus n times ln. I will have to erase this. I'm sorry about this, because I need that space. ln 1 minus ki square plus 2. This plus 2 is 2 times 1. It just increments by 1. And let me draw this again like this, the decaying thing. So every incremental thing will contribute to the previous Akaike information criteria. And there's a plus 2, so Akaike information criteria tends to increase because of this 2, but this thing is less than 1, so that's a negative pulling thing. So this as long as these negative pulling things are stronger, this plus 2 will not affect, and the new Akaike information criteria will be less than this Akaike information criteria if this is negatively strong enough. For example, if k is close to 1, let's say 0.99, then 1 minus 0.99 is 0.01, which is whose logarithm is a large negative number. So it will subtract a lot of things. Plus 2 will still be something negative, which will subtract from the previous Akaike information criteria. As long as this Akaike information criteria goes in a decaying manner, you continue. But after some time, these ki's start to become not close to 1, but they start becoming close to 0. Therefore, this becomes like ln of 1 or 1 point something, or 0.9, etc. So 0.9 logarithm is Still a negative number, but it's not a large negative number. It's a small negative number, and this +2 will make it larger. And as soon as it becomes larger than the previous Akaike information criteria, you stop there. That is the stopping criterion, which is a very nice way of making the Levinson recursion, this algorithm, to update your filter coefficients iteratively, as well as monitoring the prediction error filter order using the Akaike information criteria, using this update. And you stop when the Akaike information criterion starts to increase. I didn't do a lot of numerical examples from that. I may do one example, but not today. We will continue with the predictive coding in terms of the coding strategies next week. And before starting with the compression or coding techniques to apply the prediction, I will show you one small example of Akaike information criterion and Levinson recursion utilization together on a numerical example. That what I'm saying is this algorithm is a summary of pages long derivations, which I omitted. But even this algorithm layout is too abstract by itself. It is still not very clear. It's not a simple algorithm. It is simple, but complicated in terms of the notations. So we will see one example, one numerical example for this. And I'm emphasizing a little bit onto this one because it's not only for the compression purpose. This ACNE, the autocorrelation normal equations, ACNE, is useful for a lot of other applications. You may encounter them in another discipline as well. That's why I'm a little bit going into the details of that, and I will do one numerical example. But right now, I will stop. If you have any questions, you can ask. Otherwise, I will stop at this point, and we will continue next week. I'm not sure about the examination week. Let me first stop the recording, and then we can talk about the exam weeks.